Alright, today we want to look at limits at infinity and, of course, horizontal asymptotes, so they are related. We looked at vertical asymptotes and we talked about limits, infinite limits. Okay, so we differentiate between infinite limits and limits at infinity. So let me explain. Here's a function, and basically I want to describe this function's behavior as the x inputs get arbitrarily large in absolute value. So it could be arbitrarily large going through positive values or through negative values. And basically I'm going to use these tables to help us see the behavior. And I've entered that function, the function f, into the calculator there. You can see it. And I'm going to go to the table and I'm going to plug in 10, 100, 1,000, 10,000. Let's see what's happening. And 10,000. Okay, so let's plug these values in that I'm getting from the calculator there. 4.1048, 4.0281, 4.003, and 4.0003. Okay, well, based on our experience from finding limits numerically, now we're talking about what's happening as x gets arbitrarily large. Look at the value of the function. Is it getting arbitrarily large or small? No, it seems like it's getting closer and closer to something around 4, doesn't it? It's always a little bit above 4, but it's getting closer to 4. Let's do the same thing for negative values. Let's let the negative values get arbitrarily large. Okay, and there we see the values. I'll plug those into the table as well. Okay, and you can see the progression again as x gets arbitrarily large in absolute value, but going through negative values, negative 100, negative 1,000, negative 10,000, so on. The value does not appear to be getting arbitrarily large, but it appears to be getting closer and closer to, say, 4. It's always below 4, but it's getting closer and closer to 4. And we can confirm this by graphing. And what we're going to see is when we look at the graph of this function. Here I've graphed it from negative 10 to 10. There's actually no vertical asymptote for this function because the denominator is always greater than or equal to 5, so we're never dividing by 0. There's this little dip here, but you know, as I zoom out further from negative 100 to 100, we begin to see how this limit, all right, as x goes to through larger and larger values in the positive direction, or through larger and larger values in the negative direction, larger and larger in absolute value, that is, we're approaching, it looks almost like the line y equal 4, doesn't it? We got this little blurb here, right, where we have this dip all the way down, right? It's we kind of lost all that. You can't even see it because we've zoomed out so far away. All right. So this sort of behavior, we're going to use this notation. As x goes to infinity, that indicates that x increases without bound, and as x goes to minus infinity, we see x decreases without bound throughout all the negative values. So in this example we have up above, the limit as x goes to infinity of our function was 4, and the limit as x goes to negative infinity for our function is 4. And as we said, note that y equal 4, this is actually what we call horizontal asymptote for the graph of the function f. And so you've studied that in pre-calculus and talked about ways of finding the equation for any horizontal asymptote. So this is the way we do it in calculus then. If the limit as x goes to infinity or negative infinity is equal to a, then y equal a is a horizontal asymptote for the function. Now this tells us something about how many horizontal asymptotes a function can have. And the answer is actually 2, because these limits do not have to be the same. They can be different. Now for a lot of functions, like the function we looked at above, they are the same. The limit from as we go to negative infinity or infinity is going to be equal to the same value. And in that case, we have a horizontal asymptote. A lot of functions don't have horizontal asymptotes, right? Polynomial functions end behavior as x goes to infinity, we can be going up to infinity like x squared or x cubed. As x goes to negative infinity, we can be going up to infinity like x squared, or down to infinity like x cubed. So those functions obviously don't have horizontal asymptotes, and so they have infinite limits at infinity. Okay, let's just make sure that we're clear on this. Let's do a little graphical example of a function. I'm going to draw that function here. Here's the graph of my function. The dashed lines represent horizontal asymptotes for my function. Here's the graph of the function g. Okay. What's the limit as x goes to infinity of g of x from this graph? Well, as x gets larger and larger, as we go through larger and larger values, the graph appears to be what? Getting closer and closer, as it should be, to this horizontal asymptote, which is at what? Y equal -2. So as we go to positive infinity, we're approaching -2. As we go to negative infinity, where are we going to? We're getting closer and closer to this horizontal asymptote, which is y equal 3. And so there's our limit. Okay? So there's an example of a function that would have two different horizontal asymptotes. One as we go to positive infinity, one as we go to negative infinity. Okay? Finding limits at infinity for our basic functions is important. I just want to review that real quick. I've got the graph of some of these functions here. What's the limit as x goes to infinity of e to the x? This is the graph of e to the x. So as x goes to infinity, where are we going to? Well, we are going to infinity, right? It's getting unbounded. We don't approach any horizontal asymptote. This rapidly increases, right? As x goes to negative infinity, though, what happens? Remember, we have a horizontal asymptote of y equals 0, and we approach that as x goes to negative infinity. So as x goes to negative infinity, the limit of e to the x is 0. So these are important limits that you need to know. What's the limit as x goes to infinity of the natural log function? Here's the natural log function. Now, as x goes to infinity, this also is going to infinity, not as rapidly as e to the x, but we do have that as well. What about the sine function? I didn't graph it. I hope you all know what the graph of the sine function looks like. As x goes to infinity, right, that sine function is going from what? -1 to +1. And how long does it go from -1 to +1 as we increase x? Does it ever change out here? Does it ever change? No, it just keeps going back and forth between -1 and +1. Are we ever settling down to any particular number? Are we getting arbitrarily close to any particular value? No. This thing just continues to oscillate between -1 and 1. This limit does not exist. We don't approach anything. We don't go, it's not an infinite limit, right? I mean, these limits technically don't exist as finite numbers, but they're clearly going to infinity. This one does not. It just bounces back and forth between -1 and 1 forever. Right? So this is not approaching any finite value. Now, the inverse tangent function or arctangent function is important. Here's the graph of it. And it has horizontal asymptotes right here. Does anyone know what that is? Y equal what? It looks like about 1.5 something. Well, it turns out it's y equal pi over 2. That corresponds to the vertical asymptotes for the tangent function, right, at x equal pi over 2. This one is y equal -pi over 2. So it is important to know the graphs of the inverse trig functions, but this one in particular is important in several applications. And so, and you'll need to know this end behavior. So as x goes to infinity for the inverse tangent function, we're approaching this horizontal asymptote, which is pi over 2. As x goes to negative infinity, we're approaching this horizontal asymptote, which is -pi over 2. So those are important limits that come into play in Calculus 1 and in Calculus 2. Now, let's look at finding limits analytically, limits at infinity. One of the important limits that we're going to use is this one right here. If r is a positive constant and c is any constant, then the limit as x goes to infinity of c divided by x to the r is equal to 0, and same thing with the limit as x goes to negative infinity. And that should make sense. C is some constant. Now, it doesn't matter how big or small that constant is. X to the r, since r is positive, x to the r is going to always be getting larger and larger in absolute value as x goes to infinity. Okay? And so what's happening, we have a fixed value divided by a value that's getting larger and larger. So over time, right, the form of this limit, really, the form of this limit is going to be c over infinity, we say, because the bottom is going to infinity, right? Infinity is not a number, so we never get there. But the idea then is if I keep dividing c by a bigger and bigger number, overall this fraction is getting smaller and smaller in absolute value, right? It's getting closer and closer to 0, and in fact that's what we say the limit is 0. Same thing here. Now both of these limits we could be approaching 0. We could be approaching 0 here from the negative side and from the positive side here, depending on the constant c. But still we're approaching 0. So that's an important limit. But r, of course, has to be greater than 0. All right, let's take a look at using this now. Let's find the limit as x goes to infinity of 13 minus 70,000 divided by x. Well, first of all, I'm going to say this. The limit of a difference is the difference of the limits, and that applies to limits at infinity as well. Provided what? These two limits exist. Now what about this one? What's the limit as x goes to infinity of 13? Think about the graph of y equal 13. What's it look like? It's just a horizontal line, right? For any input, the output's always 13. As x goes to infinity, it's just 13, 13, 13, 13, right? So this is going to go to 13. What about this one here? Well, this is where we're going to use this theorem up here. Our constant c is 70,000. That's pretty big. When I plug in x equals 1, I get 70,000. X equals 2, I get 35,000. Those are pretty big numbers. But eventually, we're going to infinity. Eventually, x will get to 70,000. In that case, the ratio is 1. But then when x gets to 140,000, we get a half. And so on, right? 210,000, we get 1/3, and so on. This ratio is getting smaller and smaller. In fact, we say the limit is indeed equal to 0. So I'm using that limit there, and I get 13 is my limit. So this thing diminishes basically down to nothing as x goes to infinity. Now, let's take a look at this thing now. Up top, I got the parabola, right, opening upward, 5x squared minus 7x plus 1. That's a parabola opening upward. Clearly, as x goes to infinity, we're going up to infinity. Look at the bottom, 4 minus 3x squared. That's a downward opening parabola, right? As x goes to infinity, we're going to minus infinity. But the form of this limit, therefore, is infinity over infinity, minus infinity, doesn't matter. They're both going to infinity. That is an indeterminate form. If you remember when we were talking about finding limits algebraically, that was one of the forms we talked about. We didn't see any examples of that form, but now we do. Okay? So I don't know what this limit is. Just, you know, I can't plug in anything because infinity is not a number. Okay? So what do I do? Well, there's two ways of looking at this. Some of you already know the answer because you maybe memorized it from pre-calculus. But here's how we're going to do it two different ways. First of all, to get this theorem up here into play, I'm going to multiply this fraction by 1. I'm going to make an equivalent fraction. And it's going to be interesting because what I'm going to do is I'm going to multiply by essentially the reciprocal of the highest degree term in the denominator. Actually, the highest degree power of x in the denominator. Of course, I only have one x down here, and it's x squared. So I'm going to divide by x squared, or multiply by the reciprocal 1 divided by x squared. I'm going to do that to the top and the bottom. You say, whoa, you got to be careful. If you're 1 over x squared, that's undefined if x is 0. You're right, but x is going where? To infinity. So we're way past 0. We're looking at 100, a million, a billion, a trillion. So this ratio is always defined. All right, so what does this look like? The limit as x goes to infinity. Well, I'm going to distribute this through the top and through the bottom. 5x squared times 1 over x squared. I'm going to do this first time once. And you'll see minus 7x times 1 over x squared is minus 7x divided by x squared. And 1 divided by x squared. And down here, I got 4 divided by x squared minus 3x squared divided by x squared. But I can quickly simplify several of these fractions, can I not? 5x squared divided by x squared is just 5. 7x divided by x squared, well, one of the x's cancels. I'm left with just 1 in the denominator. That's still 1 over x squared. And then down below, 4 divided by x squared, oops, minus 3x squared divided by x squared is just 3. Okay, so I simplified that down. But then you look at our remaining fractions, and as x goes to infinity, where's 7 divided by x going to? That's going to 0, right? A constant divided by x to the first power. R is 1, right? That exponent has to be positive. So that's going to 0. 1 divided by x squared, same thing. That's going to 0. 4 divided by x squared, same thing. That's going to 0. And so what am I left with up top? 5 minus 0 plus 0 is 5. 0 minus 3 is negative 3. My limit is negative 5/3. Okay? That's the limit, making use of this relationship. Now, another way of thinking about this is, and again, when we do this, we're dividing basically by the highest degree in denominator, in the denominator. Another way of thinking about this is for large values of x, if I look at, say, the numerator, 5x squared minus 7x plus 1, when I plug in large values of x, like x equal 1 billion, right? What's 1 billion squared? It's a huge number, right? It's a huge number. 1 billion is what, a 1 with 9 zeros after it? 1 billion squared is a 1 with 18 zeros after it, right? That big number in comparison, first of all, to plus 1, that plus 1 is pretty insignificant. I mean, if you have, $1 billion squared versus $1, that's nothing, insignificant. Doesn't change anything. Really, neither does the negative 7x, right? If I do 1 billion squared versus 7 billion, 5 times 1 billion squared versus 7 billion. That 7 billion is nothing compared to that, because this is a 1 with 9 zeros after it. This is a 1 with 18 zeros after it. So it dominates. The highest degree term dominates. So what I'm saying is, as x gets very, very large, this limit we're looking at is going to look basically the same as this limit. Take the highest degree term up top and highest degree term in the bottom, right, which is negative 3x squared. This limit and this limit will essentially be the same. And notice I can simplify that down, right, because the x squareds cancel. This is just negative 5/3. And what's the limit of any constant? It's negative 5/3. Of course, we get the same thing, right? And so this is another way you can do it. It's a little less formal than what we did up here, but that's the idea of finding these limits. And some of you remember something about the fact that, notice we have a horizontal asymptote. There's a horizontal asymptote of y equal negative 5/3. And some of you remember how to do that because the degree of the top and bottom are the same. It becomes the ratio of the leading term coefficients, y equal negative 5/3. Okay. I'm going to do that same technique, though, that I used above in these last two cases. I'm going to multiply top and bottom by the reciprocal of the highest degree in the denominator, which is x to the 4th. Distribute 10x cubed divided by x to the 4th gives me 10 divided by x, right? 3 of the x's cancel with these, and we're left with 1 in the denominator. 8x squared divided by x to the 4th is minus 8 over x squared. 2 of the x's cancel with the ones in the bottom. 4x to the 4th divided by x to the 4th is 4 plus 3 divided by x to the 4th. Now what happens as x goes to infinity, then this fraction is going to 0. By that theorem above, this fraction is going to 0 and this fraction is going to 0. And so what is our limit approaching? 0 minus 0, 4 plus 0. That is determinant, right? 0 divided by 4 is 0, and that's our limit. In other words, we have a horizontal asymptote of y equals 0. And you can see that too, again, we can do it the other way. This is the limit as x goes to infinity. Highest degree term up top is that. Highest degree term in the bottom is that. And that is equal to simplifying 10/4 is 5/2, and 3x's cancel with 3 down here, leaving just 1x down here. And as x goes to infinity, then 5 divided by 2x, that's going to 0 by that theorem. Look at this one. We'll do the same thing. I'm going to multiply top and bottom by the reciprocal of the highest degree term in the denominator, which is x. So multiply by 1 over x. Again, by the way, each of these are indeterminate forms, right? Infinity over infinity. It's the same for each of these situations. But when we do this, what happens? I get 7x squared divided by x is 7x. 13x divided by x is 13. 5x divided by x is 5 minus 2 divided by x. Right? Now as x goes to infinity, this 2 divided by x is going to 0. But that's the only thing going to 0. So what do we have? We have limit as x goes to infinity, dividing by 5 or multiplying by 1/5, 7x plus 13. But this is just, if I distribute, I get what? 7/5 x plus 13/5. That's a line of slope 7/5, right? As x goes to infinity, what's going to happen? That's just going to go to infinity, right? It's just a line, right? In this case, this function doesn't have a horizontal asymptote, it actually has a slant asymptote. This actually is, this line is the slant asymptote for that function. Okay, so, and that's typically what we're going to see for these type of rational functions where I have one polynomial divided by another polynomial. That there's a horizontal asymptote, either, you know, some positive number if the degree of the top and bottom are the same, or y equals 0 if the degree of the top is what? Less than the degree of the bottom. But if the degree of the top is bigger than the bottom, then we're not going to have a horizontal asymptote. We're going to have end behavior that goes to infinity or minus infinity, depending on the situation. These cases where I have these horizontal asymptotes, if I take the limit as x goes to negative infinity, I'm going to get the same limits. These types of functions, these rational polynomial functions, have only one horizontal asymptote. But there are functions that have two, and let me show you that. So I'm going to take the limit of this function as x goes to infinity, and then in a minute we're going to do it as x goes to negative infinity. Okay. Notice again, the top and the bottom are both going to infinity as x goes to infinity, and so we're indeterminate. All right. But now this is not quite a polynomial up top with this radical. Okay. There's a polynomial under the radical, but this is not a polynomial function. Down below it is. I'm going to still use my strategy, though, of multiplying by the reciprocal of the highest power of x in the denominator, which is just x. I'm going to multiply by 1 over x, or divide the top and bottom by x. Okay? And so up top, right now I'm just going to write x squared plus 20x all divided by x. And then here I'm going to do 10x divided by x is 10 minus 2 divided by x. Now why didn't I go ahead and distribute here? Can I just divide this x squared by the x and this 20x divided by x? No, because they're under the radical. I can't do that. Okay? And so how am I going to handle this? Well, the way I'm going to handle this is by this relationship here. If x is greater than 0. Do we know that x is greater than 0 in this limit process over here? Yeah, because we're going to positive infinity, right? We're going through the positive value, so we're way in the positive realm. So this is true. If that's the case, then what is the square root of x squared? Answer, it is equal to x. Right? And that's my trick. I'm going to replace this expression here with this. I'm going to write the square root of x squared plus 20x, right? That's what was up in the numerator there, divided by x. But what's x? I'm going to replace x with the square root of x squared. Now, how does that help? Because now both are under the square root. I can now bring them both under one square root. So the square root of a divided by the square root of b, right, is the same as the square root of a divided by b. Right? That's rule of exponents. Remember, square root is to the 1/2 power. And so, what does this bring me then? The limit as x goes to infinity. And now I can bring this underneath x squared plus 20x divided by x squared. Right? So I can bring this under one radical, this stuff divided by that, all over the 10 minus 2 divided by x. And now I can divide both, right, x squared and 20x by x squared. And I get up top, x squared divided by x squared is 1, 20x divided by x squared is 20 divided by x. Okay, so all I've done is algebraic manipulations, simplifications, but now I think you'll notice, right, something. As x goes to infinity, 20 divided by x is going to what? This term right here is going to 0. 2 divided by x is going to what? 0. And so our limit is indeed approaching what? The square root of 1, 1 plus 0 is 1, over 10 minus 0, 10, which of course is 1/10. And there's our limit as x goes to infinity. Okay? Now, what happens if I take the limit as x goes to negative infinity? Well, something's going to change, and in fact, this statement here is not true anymore. I'm going to negative infinity, x is not greater than 0. So is this statement here true if x is less than 0? Answer, no, it's not. But we're going to proceed the same way. I'm going to do the same thing now. Again, this is going to be infinity over, technically negative infinity, but we'll just do infinity over infinity. It's indeterminate. I'm going to multiply by 1 in the form of the reciprocal of x in the numerator and in the denominator. And basically we get the same thing. This is negative infinity. We get the same thing that we had up here, x squared plus 20x divided by x, and then I get 10 minus 2 over x, right? The bottom's the same. But this x now, can we just replace it with the square root of x squared? No. So what's going to be true this time? If x is less than 0, then x is not equal to x squared. And the reason is, just check any negative number out, like negative 2. If I plug in negative 2 for x, then this side over here is negative 2. But if I square negative 2, what do I get? Positive 4. What's the square root of positive 4? 2. Does negative 2 equal 2? No, it does not. So this is not true. In order to make this true, there's a couple things we can do. But what we're going to do is this. We're going to multiply by negative 1 here. Okay. Another way is to use absolute value of x. That's really the true statement. The square root of x squared is actually equal to the absolute value of x. That will work for any value of x. But I want to do it this way, and now it works, right? Because over here we said if I square negative 2, I get 4. Square root of 4 is 2. But now I'm going to get negative 2. And negative 2 would be equal to negative 2. So the only difference is, right, I'm going to replace x with this thing. Then the only difference compared to what we have up above, right, is that there will be a negative 1 outside here. Right, negative 1 outside here. All right, so this will be negative outside here. All right, so let's just do that. The limit is x goes to negative infinity. So I've got the square root of x squared plus 20x now over negative the square root of x squared. And now I can bring these under, divide this way, but this negative sign is going to make the top negative. So it's going to be negative the square root. Now x squared divided by x squared is 1. 20x divided by x squared is 20 over x. So everything's the same. It's just this negative 1 out here that is different in this case. And now as x goes to negative infinity, again, this is going to 0, and this is going to 0. And therefore my limit is what? Up top, negative the square root of 1 over 10. So my limit is negative 1/10. And that's different than the limit going to positive infinity. And so our function here, that we're taking the limit at positive and negative infinity, has two horizontal asymptotes. Okay? So, lots more examples to try in the homework, and encourage you to do that. We're pretty much done looking at the limit process, but in the next video we are going to talk about a nice little thing called the intermediate value theorem, which is pretty obvious. It's connected to functions that are continuous, and it's very useful in solving, we'll see, equations. So we will do that in the next lecture.